Hello, welcome to Lecture 5 of Circuits 1. Last time we talked a little bit, just briefly at the end of lecture, about series and parallel circuit elements. We're going to do a quick review of what that definition is and what it means. We'll use that concept to go on and talk about circuit reduction, which we also mentioned last time as being a way to reduce the number of overall unknowns in our circuit. Our related educational module is section 1.5. Okay, series and parallel circuit elements. Circuit elements are said to be in series if they carry the same current identically, if they always have the same current. For example, if I do KCL at node A here, I'll find that the current I1 is equal to the current I2 always. So those can be replaced with a single unknown I, and then we have eliminated one unknown from this system. Elements are in parallel if they have the identically same voltage drop. These two elements both share nodes A and B. If I do KVL around the single loop that is here, I find that minus V1 plus V2 is equal to 0, so V1 is equal to V2. Those can be replaced with a single variable V. I don't need to track two different variables for the voltages of these elements. Recognizing these combinations of elements can allow us to use a circuit analysis technique called circuit reduction. What we do is combine elements that are in series or in parallel in order to reduce the overall number of elements in the circuit. Once we've reduced the overall number of elements, that allows us to reduce the number of unknowns. For example, in the parallel configuration we saw before, we could replace the two variables V1 and V2 with a single variable V. That can simplify our life significantly. Let's take a look at a quick example of this kind of technique. For this particular circuit element, anywhere in here that I do KCL, for example, if I have a current I1 here, KCL at this node tells me that the current through this voltage source is also I1. If I do KCL here, it also tells me that the current through this resistor is I1. So KCL applied at any point in this circuit leads me to the conclusion that the currents everywhere in this circuit are the same. They can all be specified by a single variable name I. So anywhere in this loop, the current is I. So in words, if I apply KCL at any node, I can find that every one of these elements has the same current all the time. These elements are all in series. This is a series combination of circuit elements. Now let's take a look at applying circuit reduction analysis techniques to a simple series circuit. This is the same circuit that we had on the previous slide. On the previous slide, we decided that the current in any of these elements was always I. So we'll use a single variable name I to denote the current in all these elements. If we do that, then we know that the voltage difference across R1 is, by Ohm's law, I times R1. The voltage difference across R3, for example, is then going to be I times R3. The voltage difference across R4 is going to be I times R4. Now notice my polarity on these voltages. I've always assumed on the previous slide that current was going in this direction around the loop. Once I've assumed the current direction in each of these elements, my voltage polarity for Ohm's law has to be set up so that current's entering the positive voltage node. That means this voltage node has to be positive, this voltage node has to be positive, and this voltage node has to be positive. Now if I apply KVL around this loop, starting at the lower left-hand corner, coming up here, I hit the negative terminal of V1 first, which gives me a negative V1. I hit the positive terminal of I times R1, so the voltage difference across R1 is positive IR1. This positive voltage terminal is first, so it's a plus V2. I times R2, which I didn't label, Then I times R3, I hit the negative terminal of V3 next, so that becomes a negative V3 and a positive I times R4. Then I'm back to my starting point. That sums up to 0. I can regroup these to group the voltage sources together. So I have a negative V1, a positive V2, and a negative V3, and the current I multiplies the sum of all the resistances. Now I could equivalently write this circuit as an equivalent circuit with a single equivalent voltage and a single equivalent resistance. The current through this circuit is the same as the current through this circuit. They're both I. Now, if I do KVL around this, I get minus VEQ plus I times REQ is equal to 0. So VEQ becomes the negative of this. REQ is the sum of all of the resistances. So we can combine these circuit elements to get an equivalent, simpler circuit. So from that specific example, I'm going to infer some kind of general rules for series circuit reduction. If I have voltage sources in series, they add directly in order to create an equivalent voltage source. You need to keep track of the voltage polarities on the individual voltage sources, however, so that those are preserved in your final equivalent voltage. Resistances in series also add directly. Since resistors always dissipate energy, you don't necessarily have to worry much about polarity there. They will always add up. Let's use those analysis techniques now to analyze a simple circuit. We want to determine the power that is delivered by this 20-volt source. In order to determine that, I need to find the current out of the source, which I'm going to call I. Now, KCL at any point in this circuit will tell me that the current in all of the circuit elements is the same. These elements are all in series. Thus, we do not need individual unknowns to represent the currents in each of these resistors. They are all the same. They are the current I. Now if I do KVL around this loop, starting at this lower left-hand corner here, I hit the negative terminal of this source first, minus 20 volts, plus the voltage drop across this resistor is 2 ohms times this current, plus the voltage drop here is also 2 ohms times the same current. I hit the positive terminal of this voltage source first, which gives me a plus 4 volts, and the voltage drop across this resistor is going to be its resistance 4 ohms times that same current. Those all sum up to 0. Now I've managed to write one equation in one unknown. It's what I want to determine. Minus 20 plus 4 is minus 16 volts, plus 2 and 2 is 4, plus 4 is 8 ohms times I, so I is equal to 2 amps. I got a positive current. That means current is indeed going in my assumed direction, so current is leaving the positive voltage node. That means that the power generated by this, the power is going to be negative that comes out of this. It's going to be generated. Therefore, P is equal to 20 volts times minus 2 amps. Those disagree with the passive sign convention, which is a minus 40 watts. We could do this problem a different way. We could take this overall circuit and just simplify the circuit. We could write this circuit as a voltage source, which has a voltage difference of plus 20 volts here. This polarity is the opposite to this, so 20 volts minus 4 volts is an equivalent 16 volt source. I can put that in series with a resistor, REQ, which is the sum of the individual resistances. 2 ohms plus 2 ohms plus 4 ohms is 8 ohms. The current through this circuit will be the same as the current through this circuit. So I is equal to 16 volts over 8 ohms, which is 2 amps. That's the same result we got previously. The power output from the system will be the same. Now let's take a look at another kind of special case, but it is general in the sense that we've given ourselves an arbitrary number of resistors. What we're going to do is take a series combination of n resistors. They have resistance R1, R2, up through R sub n. We're going to develop an equation called a voltage divider formula that will allow us to determine the voltage across any arbitrary resistor in this series combination. We've already noted that these resistors are in series. They will all have the same current I. If I do KVL around this loop, I will find that minus V sub S plus I times the sum of all the resistors, R1 plus R2 plus all the other resistances in this series combination, plus on down to R sub n, is all equal to 0. If I solve this equation for I is equal to V sub S over the sum of all the resistances. Now I can use this equation and Ohm's law to determine the voltage difference across any individual resistor. If I want to look at the kth resistor, I multiply this current times R sub k. So V sub k is equal to I times R sub k. I is this, so V sub k is equal to V sub S, pulling that out front, times R sub k over the sum of all the resistances. What this is telling us is that the voltage drop across the kth resistor is in the same percentage to the total voltage drop as this resistance is to the total resistance. That point is important enough to reiterate again. This is what is called our voltage divider formula. The kth voltage drop across resistor R sub k is just the total voltage drop across all the resistors that are placed in series multiplied by the kth resistance and divided by the sum of the total resistances that are in series. So the ratio of V sub k to the total voltage drop is the same as the ratio of R sub k to the total resistance. There's a very common special case of the voltage divider formula that gets used a lot. It's the case in which you have a single voltage source in series with two resistors. If I want to determine the voltage drop across R1, which I have called V1, this voltage is the total voltage drop times this resistance divided by the total resistance. So it is going to be V sub S times R1 over R1 plus R2. Likewise, if I'm interested in the voltage drop across resistor R2, its voltage is simply the total voltage drop, V sub S, times R2 over the sum of the two resistances, R1 plus R2. Those equations are worth memorizing. Now let's use our voltage divider formula to determine the power dissipated by this 2 ohm resistor. Take a quick look at this problem on your own, come back and I will solve it for you. Now I can use my voltage divider formula very easily to determine the voltage across this resistance. Once I've got the voltage drop across this resistance, I know that the power dissipated by that resistor is that voltage squared divided by the resistance. So let's call this V. So my voltage divider formula tells me that V is going to be the total voltage, 20 volts, times this resistance, 2 ohms, divided by the total resistance, which is 2 ohms plus 3 ohms. So this is 20 volts times 2 over 5, which is 8 volts. And the power is equal to V squared over R, which is going to be 8 squared over 2 ohms, which is 64 over 2 or 32 watts. Resistors always absorb power. Now, if you didn't notice that this was a voltage divider, it's no big deal. You could also choose to determine the current through this circuit and then use power is equal to I squared times R. So alternately, okay, if you recognize that these are in series, the current I is just the total voltage over the sum of the resistance. So an equivalent circuit is plus minus 20 volts times the total resistance. Req is 3 ohms plus 2 ohms is 5 ohms. Ohm's law tells me that I here is 20 volts divided by 5 ohms, or 4 amps. Once I know the current, I can determine the power dissipated by this. P is equal to I squared times R, which is 16 times 2, which is 32 watts. Maybe a little bit more work, but not a whole lot. Okay, one more simple example of voltage dividers. We want to determine the voltage V1, the voltage across this 4 kilo ohm resistor in this circuit. Hopefully this is now easily recognizable as a series combination. Try using your voltage divider formula to determine this voltage difference. Come back, I'll work through the problem. Now, hopefully by now you're getting pretty good at identifying the fact that these elements are all in series. Once they are all in series, you can use a voltage divider to determine an individual voltage in that series combination. So V1 is going to be the total voltage drop across the series combination, which is 12 volts, times the resistance, where V1 is taken across, 4 kilo ohms, over the total resistance in the series, which is 10 kilo ohms plus 4 kilo ohms plus 4 kilo ohms plus 6 kilo ohms. Let's see, 4 and 6 and 10 is 10, 10 and 10 is 20. This is 24. 4 over 24 is 1 over 6. This is 2 volts. Easy to do if you recognize this as a series combination and apply the appropriate voltage divider formula. Now let's shift gears and talk about parallel combinations of circuit elements. We're going to develop the same types of relationships that we did before with series circuit elements, except this time the circuit elements will be in parallel. We'll start out just in terms of a simple example, and we'll go on and generalize the relationships from there. For this particular circuit, if I do KVL around any of these loops, I will find that the voltage difference across each of these elements is the same. Okay? I can assign that a single variable named V. I don't need to keep track of, in my equations, the different voltages across the different elements because they're all the same value all the time. So, if I apply KVL around any loop, all of these voltages will turn out to be the same all the time. These are all in parallel by definition. Now we're going to use the circuit from the previous slide to show an example of circuit reduction using parallel circuit elements. If I apply KCL at this upper node, knowing now that the voltages across all of these elements are the same, and if I assume that positive currents are leaving this upper node, I1 is going into the node, it becomes a negative contribution to the current at that node. The current through R1 is just V over R1. Since my positive voltage node is at the upper node, it has to be positive. I2 is going out of the upper node, it becomes a positive I2. V over R2 is the current leaving the upper node through resistor R2, and then V over R3 is the current leaving the upper node through resistor R3. I can group these terms into source terms plus terms multiplying this resistance. I get a negative I1 plus an I2 as our overall source, And then voltage multiplies 1 over R1 plus 1 over R2 plus 1 over R3. That sums up to 0 from the above. This equation is the same one that I would get by rewriting this as an equivalent circuit with a single source and a single equivalent resistance. In this particular circuit, if I do KCL at the upper node, I get minus IEQ plus V over REQ is equal to 0. So IEQ becomes this combined source term over here, and 1 over REQ becomes 1 over R1 plus 1 over R2 plus 1 over R3. A few notes relative to reduction of parallel circuit elements. From the previous example, we saw that current sources which are in parallel add directly to form an equivalent current source. You do have to account for the directions, however, so that you know whether to add or subtract each individual current source to get the total. In order to interpret our previous results in terms that are consistent with our approach towards series circuit elements, I want to define a new term. Conductance is the inverse of resistance. Conductance is generally denoted as G, so the conductance of a particular resistor is just 1 over the resistance value. Using conductance in Ohm's law implies that now I is G times V. Now, units of G are either Siemens or Mohs. Mohs is just ohms spelled backwards. Those are abbreviated as S or an upside down omega to denote that it's 1 over the regular omega that we use for resistance. From the previous results, we can see that conductances in parallel add the same way resistances in series add. Now let's revisit our previous example in terms of conductances to kind of illustrate the points that I made on the last slide. Resistance R1 has a conductance G1, which is 1 over R1. Resistance R2 has a conductance G2, which is 1 over R2, and resistance R3 has a conductance G3, which is 1 over R3. Now we can do KCL at the upper node in terms of these conductances. So I have I1 going into the upper node. I'm going to assume that currents into the node are negative. Plus, I now have V times G1. Gives me the current going through resistor R1. I2 is coming out of the upper node. That is a positive contribution in my version of KCL. The current going through here is G2 times V. The current going through R3 is G3 times V. That sums to 0. So now we have negative I1 plus I2 plus V times G1 plus G2 plus G3 is equal to 0. We can now rewrite this as an equivalent circuit in terms of the conductances. So we can have this rewritten as an equivalent I with an equivalent G representing our resistors, and GEQ is the sum of the individual conductances. Now let's do an example of applying our previous parallel circuit reduction techniques to solve a problem. We have a parallel combination of circuit elements. It's extremely similar to our previous example, except that we have provided values for the resistances and the currents. We want to determine the power delivered by this 2 amp source, So if we can determine the voltage across this source, we can determine the power. Try using your circuit reduction techniques to determine the power across the 2 amp source, then come back and let me have a shot at doing the problem. Okay, consistent with my previous approach to this similar problem, I'm going to do KCL at this upper node, and I'm going to assume that positive currents leave the node, therefore this 2 amp current will be considered to be negative, so negative 2 amps plus the current through the 2 ohm resistor is this voltage divided by 2 ohms. This 1 amp current is going into the node, which makes it a negative contribution. The current through the 6 ohm resistor is the voltage difference across the resistor divided by 6 ohms, plus the current through this 3 ohm resistor is the voltage difference over 3 ohms. That sums to 0. Doing some simplification, negative 2 amps minus 1 amp is negative 3 amps. I'm going to take that over to the other side and make that a positive 3 amps is equal to V times 1/2 plus 1/6 plus 1/3. Therefore, 3 amps is equal to V times 1/2 is 3/6 plus 1/6 is 4/6 plus 2/6 is 6/6 or 1. So V is equal to 3 volts. The fact that this is positive means that my assumed sign convention is correct, so my current is entering the negative voltage node, which disagrees with my passive sign convention. So my power is 2 amps times a relative minus 3 volts, or minus 6 watts. This element is generating power. Now let's look at a process called current division. What we're going to do is take a look at a parallel combination of N resistors, so a fairly general setup, which have a single current I sub S flowing into this parallel combination. We're going to want to find the current I sub K through some arbitrary resistor in this combination. Consistent with our previous analysis, KCL at this upper node says that I sub S going into the node is equivalent to the sum of the currents coming out of the node. So I sub S is equal to, if this voltage difference is V, V times 1 over R1 plus 1 over R2 plus the currents through all the other resistors up to 1 over R sub N. Therefore, V is equal to I sub S times 1 over R1 plus 1 over R2 plus 1 over R sub N. I'm dividing both sides by this quantity. Now, I sub K is just this voltage over the kth resistance. Therefore, I sub K is I sub S times 1 over R1 plus 1 over R2 on up to 1 over R sub N times 1 over R sub K. Next slide, I'll summarize this. Now, just to summarize our current divider formula in which we're determining the current through an arbitrary resistor in a series of N resistors which are placed in parallel with one another. Previously, we determined that the current through the kth resistor is the total current into this parallel combination times 1 over R sub K divided by the inverse of each of the individual resistances all added up. That's probably better expressed in terms of conductances. I sub K is also I sub S times the conductance of the kth resistor divided by the sum of the conductances of all the resistors in the parallel combination. So now using this equation, we can kind of summarize our current divider formula the way we did our previous voltage divider formula. So the ratio of I sub k to the total current into a parallel combination of resistors is the same as the ratio of the conductance of this resistor, G sub k, divided by the total conductance of the parallel combination. I will tend to default to this formula rather than explicitly calculating conductances, though. Now let's look at the special case of two resistors in parallel. With a known current going into this parallel combination, I'm going to create a special current divider relationship for these two resistors. This circuit can be rewritten as an equivalent circuit with a current going into an equivalent resistance. As we said before, this conductance adds these two conductances directly. The resistance is 1 over the sum of the conductances. Okay. Clearing the denominator, multiplying top and bottom by R1 times R2 gives me Req is R1 times R2 over R2 plus R1. So the equivalent resistance of a parallel combination of two resistors is the product of the two resistances, R1 times R2, over the sum of the two resistances, R1 plus R2. Now, if we want to find the current through resistor R1, I1 is the voltage difference V over R1. This voltage is this current times Req. That is I sub S times 1 over R1 plus 1 over R2 times 1 over R1. This becomes I sub S times 1 over R1 divided by 1 over R1 plus 1 over R2. Multiplying top and bottom by R1 times R2 gives us I1 is I sub S times R2 over R1 plus R2. So for a parallel combination of two resistors and only two resistors, to find the current in one resistor, you multiply the total current times the other resistance divided by the sum of the two resistances. Correspondingly, if I want to find I2 is the other resistance, R1, over the sum of these two resistances times I sub S. So I2 is the total current times the other resistance over the sum of the two resistances. Okay, let's use our current divider formula to determine the current in the 2 ohm resistor. We want this current. If we're going to use our current divider, we need to determine the total current in and then use a current divider to find this current from that total current. Take a shot at that, come back, then you can watch me do it. Okay, to find this total current, which I'm going to call I sub S is going to be this voltage divided by the equivalent resistance here. I can redraw this circuit as a 3-volt source in series with an equivalent resistance. Req from our previous slide is the product of these two resistances, 2 ohms times 1 ohm over 2 ohms plus 1 ohm. So Req is 2 ohms over 3 ohms, so Req is 2/3 of an ohm. Now, this current, I sub S, is V, 3 volts, over Req, which is 2 over 3 ohms, or 9 over 2 amps. Now that I have I sub S, from my current divider formula, I is the other resistance, 1 ohm over the sum of the two resistances, 2 ohms plus 1 ohm, times the total current going into this resistor, 9 over 2 amps. So this becomes 1 over 3 times 9 over 2, so that I is 3 over 2 amps, or 1.5 amps. Now, if you're doing this problem on your own and you said, why the heck is he doing a current divider formula? Congratulations. I don't need to go to this much work. I know that the current through a resistor by Ohm's law is the voltage across the resistor divided by the resistance. So directly from Ohm's law, I could say that I is equal to 3 volts over 2 ohms, which is 3/2 of an amp. Luckily, we got through the previous process okay, but there's much less chance for mistake in this approach. It's always worthwhile to stare at the problem for a while, see if there's an easy way to do it. Let's do another example. We want to determine a value for this resistance that causes the current through this 1 kilo ohm resistor to be 2 milliamps. The total current going into this current divider is 3 milliamps. This is an extremely good application for a current divider formula. I is the total current into the combination times the other resistance over the sum of the two resistances. Okay. We want I to be 2 milliamps. Okay, so R over 1 kilo ohm plus R is going to be 2/3. Therefore, R is equal to 2 kilo ohms. Okay, our next major topic is going to be circuit reduction. I want to reiterate what that is right now and do one quick example. Then next lecture we'll do a lot of examples of circuit reduction. We've noted that series and parallel combinations of circuit elements can be combined into equivalent elements. That combination reduces the number of elements in the overall circuit, thus it reduces the number of unknowns in the overall circuit. So the circuit, in some sense, becomes simplified. That can often be analyzed more easily than the original circuit. An example circuit reduction problem. We want to take this example circuit and determine the current through the 2 ohm resistor. Now, way back in lecture 3, we did this example using KVL, KCL, and Ohm's law. We did an exhaustive approach in which we wrote 6 equations and 6 unknowns. We never even bothered to solve them. We were just happy writing that many equations. Now we're going to take a look at simplifying this problem by combining circuit elements. What you want to do is see if you can find parallel combinations and series combinations of elements and simplify the circuit by combining those combinations and then analyzing the more simplified circuit. Take a quick look at the problem, come back, I'll work through it for you. Okay, I can identify these two 4 ohm resistors as being in parallel. They share the same pair of nodes. If I do KVL around this loop, it will tell me that this voltage and this voltage are always the same. Therefore, I can take these 2 resistors and combine them into a single equivalent resistance. I'll do this problem in multiple stages. I'm going to retain my 10-volt source. I haven't done anything with my 2 ohm resistor yet, but I'm going to replace these 2 resistors with a single equivalent resistance. For the special case of 2 resistors in parallel, the equivalent resistance is the product of the 2 resistances, 4 times 4, over the sum of the resistances, 4 plus 4, 16 over 8 is 2, so the equivalent resistance is 2 ohms. I can now take this equivalent resistance here, Notice that the equivalent resistance here now looks like two resistors in series. So I have a 2 ohm resistor in series with another 2 ohm resistor. I can combine those to give myself another equivalent resistance. Resistors in series add directly, so this series combination is 2 ohms plus 2 ohms, or 4 ohms. The current I through this resistor is the same as the current I through the 2 ohm resistor. So the current through this REQ is the same as the current that I want. I is equal to the voltage difference, 10 volts, over the resistance, 4 ohms, or 2.5 amps. Okay, in the next lecture, we'll primarily just do more examples of circuit reductions. Identifying these series and parallel circuit elements and combining them appropriately tends to just take some practice in doing it. So I'll go through a bunch of examples. Hopefully that will give you a database from which you can continue to do problems on your own.